Hi everyone, I'm Lauren Lusk.
And I'm Sam Shebert.
And this is our presentation on 4G and 5G signal classification. So our objective is to classify the signal standard of an unknown wireless signal, be it 4G, LTE, or 5G. Part of our motivation is the trend towards spectrum sharing and dynamic spectrum access in wireless communication. It's useful for smart communication systems such as cognitive radio to identify interfering signals in order to choose an optimal transmission strategy. This also has military application such as identifying unknown signals, whether they be enemy, ally, or neutral. Looking at the literature, there are many different types of models that are used for signal classification. Here are a few of them, as well as the features that are fed into those models. All of the work that is presented on this slide does not necessarily classify 4G or 5G wireless signals. Many of them actually do some sort of amplitude modulation, frequency modulation, shift keying, and other types of digital as well as analog modulation. As you can see, there are several different papers that have used convolutional neural networks, and there were a few that used a support vector machine. So we decided to use those two in order to get a better sense of how they work and what's being done in the field.
So we chose to generate our own data set, and this was mainly because there's not a lot of data sets available for wireless communication. So we used MATLAB using the LTE and 5G toolboxes to generate signals. We generated about 3,000 signals total, with half of them being 4G LTE and half of them being 5G. So each signal is one radio frame, which means it's 10 millisecond duration. And each signal is a unique combination of signal parameters. So some of these parameters are bandwidth, which was varied from 1.4 to 100 megahertz. Modulation, which goes from QPSK to 256 QAM. The utilization of the total amount of data that could be transmitted in the radio frame was varied from 0 to 100%. And then there's also some additional parameters that were varied. On top of this, there was random transport data for every signal and random resource block allocation. So before we could use the data set for training, we had to do some signal processing on it. So the first thing we did was upsample all of the signals to 122 megahertz. And this was because the largest bandwidth signal needed this sampling rate. So in order to have the same sample rate for each signal, so each sample is worth the same amount of time, we upsampled everything to the highest sample rate needed. And this meant that each radio frame signal is 1.2 million complex samples. So after this, we took a random subsample of each radio frame signal. So we did this for a couple of reasons. The first being it's more realistic due to a random starting time. So in the diagram, if this was a radio length frame signal of 10 milliseconds, we choose a random start time to start sampling it. And it also reduces the amount of data as the second reason, because we're taking a subsample of the entire signal. So basically we take a random start point and we take a subsample of some duration, and then based on that chunk of the signal, we would try and classify what class the signal is. And then after this, we add impairments to the signal. So we add additive white Gaussian noise, a frequency offset, and an IQ imbalance with random degrees. And the reason we do this is to better emulate what over-the-air signals would look like if you captured them. So just a visual to get a better understanding of what these impairments are. In the top left, there's a complex exponential, the blue line being the real part, the orange line being the imaginary part. Moving to the top right plot, we can see what an IQ imbalance looks like. So the real part of the signal became larger than the imaginary part. It also could be the other way around. The imaginary part is bigger than the real. Moving to the bottom left, this is a frequency offset. So you can see that the frequency of the sinusoids is increased. And then moving to the bottom right is what additive white Gaussian noise looks like. And this is where you add noise based on a Gaussian random variable with zero mean.
So these are the models that we tested. We did a 1D convolutional neural network, a 2D convolutional neural network, a feed-forward neural network, and a support vector machine. So this figure on the slide is a representation of a general neural network where n is the number of features, I is the number of hidden layers, and k is the number of neurons in each layer. So for the 1D and 2D convolutional neural networks, we used 3 convolution and pooling layers and 3 dense layers. And for the feed-forward neural network, we used 5 dense layers. So this image is a visualization of how a support vector machine works. The objective of the support vector machine is to find a hyperplane in n-dimensional space that distinctly classifies the data, where n is the number of features. It tries to maximize the margin, where the margin is the distance between that hyperplane and the nearest data points.
Okay, so this was our primary result. It's a plot showing the accuracy versus the signal to noise ratio of the additive white Gaussian noise that was added to the signals. So first thing that we can see is that the deep learning models outperform the SVM across the board at all SNR levels. We can also see that as the SNR drops, the accuracy drops, which makes sense because as you get to like a minus 20 dB signal, the signal is significantly higher power of noise. So the signal is basically completely noise at that point. And then looking a little bit closer at the deep learning models, we can see that the 2D convolution performed the worst. And this might be because the data that we have isn't really naturally 2D data. It's a 1D time series signal. You can see that the 1D convolution outperforms that, and then the top, pretty close to the 1D convolutional network, is the feed-forward network. So in conclusion, we see that the deep learning models outperformed the support vector machine. Overall, we would say that the 1D convolutional neural network performed the best, even though it had a slightly lower accuracy than the feed-forward network at 98.8% at 20 dB. The feed-forward network had a little bit of overfitting, which we don't have a lot of time to talk about now, but in the paper we can go into a little bit more depth about that. Another thing is that the IQ imbalance and frequency offset didn't really cause any large effect on the accuracy of any of the models. It was mainly just the Gaussian noise that had a large effect. And then looking at some future work, adding more classes would probably be the first thing to do. So, add in Wi-Fi signals, radar signals, and any other wireless signal you'd want to be able to classify. And then maybe looking at a transfer learning problem where, since we have a lot of data, synthetic data we can generate, that is pretty good, and not a lot of actual over-the-air captured data. It might be interesting to train the models on all the synthetic data and then maybe train it at the end on a little bit of the over-the-air data and see if that would give better performance than solely one or the other. So that concludes our presentation. Thank you for listening.